Good evening, ladies and gentlemen. I've been working on tonight's video for coming up on 2 weeks, so hopefully this goes off without a hitch. What we're talking about is the Futures Crate, recently released, I don't know if it was released or not, by Alex Crichton. I'll look at crates.io real quick and see if it's actually up there or not. Yes, I think. An implementation of futures and streams featuring zero allocations, composability, and iterator-like interfaces. So it looks like it's actually up there. All right. So I actually was testing this, but I pulled it from what do you call it? From just Git. So I'll probably still pull it from Git whenever we do this. Cargo new bin. All right. So sorry, I'll make this bigger. Futures is actually kind of a, I don't know, a common sort of a paradigm in, maybe futures are a common paradigm in modern programming. The idea that you start an operation and then you can compose that operation with other operations that depend on that operation without that operation having completed yet, basically. I think in JavaScript that's called promises. I'm not really familiar with what it's called in anything else other than Rust. The biggest reason for that being just that in C# we have the async or the task parallel system, and I'm kind of used to just calling these things tasks, basically. The one thing about this in Rust is that these can all happen on the same thread in Rust. They don't necessarily involve other threads. So, I don't know. Maybe the best thing to do would be just to read Mr. Crichton's description. Homepage. A major piece, or a major missing piece of the Rust ecosystem has been how to work with asynchronous I/O and in general composing many I/O tasks together in a lightweight way across libraries. Futures have worked out fantastically in other languages to solve this same problem, and they also kind of turn out to be a great way to solve this problem in Rust as well. One thing about Rust that I thought was a little bit strange, and which you'll kind of get a better sense for as we continue this video. In Rust, futures are, he had a specific term that he used. I'll see if I can find it. Designing futures, here we go. He talks about how these things compile from like a complicated higher level representation down to basically a very simple state machine. Here we go. So normally futures are what we call completion based. There's a very standard way to describe futures, which we find in virtually every existing futures implementation. A function that subscribes a callback for notification that the future is complete. I'm reading and paraphrasing because my eyes won't focus on the screen. Should have taken out my contacts before I started this. That's not what we're doing. What we are actually doing is what he terms a demand-driven or readiness-based implementation. And basically what that means is you continually, or not necessarily continually, it's actually customizable, but your task will poll the future to see when it completes. And that is probably the #1 weirdness about this whole thing. We're going to have to wrap our heads around that in order to get this implementation done. So, here's the plan. We're going to write that. Only we're going to do it using futures and allowing the user to input a name beforehand. Well, not beforehand. We're going to make it so that the program asks the user to input a name and has a timeout. So I guess the basic idea is we're going to take the one of the operations from the there's a tutorial, and this tutorial shows at one point, it's not exactly like featured or anything, but it shows having a timeout, I think, or not. Maybe it was in a different page. Whatever. Anyway, it shows a timeout, but it doesn't show an implementation of one, so I thought, well, that sounds like a cool use for this. I'll implement a timeout, and we'll go from there. So that's exactly what we're going to do tonight. This is going to be a fairly long video, I expect, but I do have all of my research and everything ready, so I'm going to try to squeeze this into as little time as possible. But it's a fairly, I don't know, complicated thing, so we'll see. First thing we do is import the crate, of course. I'm going to create two modules here. One to get the input, and one to create the timeout struct, basically. Hope I spelled that correctly. Don't really know. So the timeout struct as I envisioned it originally was pretty simple. It basically consisted of an epoch, which is what I called it. I don't know what you would actually call it. A timestamp. It consists of a timestamp and a duration. I think in Rust terms we're talking about, and this is one of the few times I've ever used standard time, duration and instant. And the basic bones of the class were that and that. That's it. The only thing was that I found as we went on that in order to compose a timeout as a future, I needed to have both a positive and a negative return type, basically an error and a result, or an OK and an error case, basically. And so that kind of made things grow a little bit. And so we have here an error type E, and we're going to provide an implementation only for the error type E where I'll do that later. Only where it provides the right kind of stuff, basically. And the last thing that I found out is that in order to have a return type at all, we had to have some kind of return. Specifically, just a phantom marker to say this is what this would be if we were going to return anything, but we're not. And I'm basically doing this because it seemed to me like creating an error was a fairly expensive operation, at least when we're talking about an I/O error, which is what we're talking about here. And I wanted to defer that until it was actually required. So rather than having an actual error, I am deferring that error until later. Oh, yeah, no, I can skip that. My original implementation has a third type, the error type, as well as the error function type. And since I'm declaring the error to be specific here rather than, a type thing, I can skip that here. All right. Sorry, I'm trying to get a little bit better view of what's going on. You're supposed to have a line at the end. What does the matter with you? Okay. So there's our constructor for the timeout. It's pretty simple. It just fills in all those fields. This needs one method, I think. And all this method does is compare the time elapsed since the timestamp to the intended duration of the timeout. If the time elapsed is equal to or greater than the intended duration of the timeout, then, well, it's elapsed. All this is pretty simple. We've not even touched the future stuff yet. We're about to implement futures for the timeout, but let's go ahead and jump over to main here and kind of put together the bones of how we're going to do this. So, we're going to start by just matching on the read operation. One thing we might get back is nothing. In that case, we're going to say hello, whatever your name is. Or if we get a name, there we go. Obviously we need to read name. I don't know why I do that. There we go, I have a result string. Okay, so in order to do this part, we're going to have to compose the timeout we've just created with something else. Specifically, what we're going to compose it with for right now until we actually get this implemented is the never type, I think. Or empty. I think it's called empty. I'm going to check the documentation real quick because I don't want to lie to you. Yep, okay. So we'll compose this with empty, or we'll just start with empty. Oops. Oh, that's already imported because of the crate import up above. And upon reflection regarding what somebody said on one of my videos probably a week or two ago now, in spite of how silly this seems to me, turning a string into a string, I think that for my viewers, it will be clearer if I just do it. Normally I would call to owned on this, but whatever. So what this select does here is it says, give me the first of these two futures that completes, along with the other future. That's what it boils down to. And what that looks like is a little bit strange, I think. What we have is match result. And this right here, this is a tuple, right? This right here is either a task or another future, and I can't remember which. I think it's a task with the other future running on it. Let me look. Okay, yeah, it's another future. So whichever one completes first is going to appear here in theory, and the other one is going to appear here. But one thing that we know for sure is that this timeout can't return anything good. It's only going to return this IO error. So we're going to catch that down here. And in either case, we're going to just ignore the other future completely and drop it at, when we leave this scope, because we're no longer interested in the other one. So in order for this to compile, we have to actually go implement, obviously, the future trait on the other thing. Now, like a lot of traits in Rust, this one is pretty convenient to implement. It only requires one method to be implemented. So where E is some function returning, well, no, that's not right. I don't know how I got that habit, I guess. Where E is some function returning an IO error, implement future for timeout. I forgot to type future. First thing we start with is, type item t type error equals IO error. The only method you have to implement is this one, and mute self poll. Now, before you get too far into this, poll is actually a type alias, and it's not even a particularly complicated one. It basically boils down to a result of type async and E, or async T and E. But whatever, I didn't want to type that out, so I'm typing out the other thing. Which of course means that I have to import future and poll up here at the top of the screen. There we go. Once we're in here, I'm going to import a few other types too, because they'll just make things easier for me. The task is actually a namespace from which we're going to use a couple of different functions. Okay, so the only thing we want to check in this poll method is, has the timeout elapsed? So if it has, we return an error. That being whatever this method creates. Otherwise, we say Not ready. Try again later. But there's a catch. And this is what made me take so long to get through with this, because I had to find the will somewhere deep down inside to actually go dig through all the code for an example of how this was done. And yeah, had other things to do. What you actually have to do here is park the task and unpark it. I don't know why. To me, this is black magic. But what this is telling the task to do somehow, the task being the thing that runs this future, the thing that drives it to completion, as the documentation says, this tells the task to come check this again. If you don't add this line in here, if you take this out, then this pull will only happen once. And needless to say, the timeout will not have elapsed and nothing will ever happen. Your program will never stop running. So, do this. This part is important. But that's the entire implementation. It's not that complicated. All we're doing is saying, are we done? If not, then try again later. So let's see what that looks like. Make sure that it actually does something. What should happen here is it should spit out hello whatever your name is here in, I don't know, 10 seconds after it finishes this. I probably shouldn't have set that to 10. It's going to be very boring television. Oh, never mind. Yeah, there's not supposed to be a semicolon there. What is wrong with you? Where else did I put one that I'm not supposed to have one? Okay. Undeclared type or module timeout. Oops. Try that again. It's probably going to complain that duration is not in here. Yeah. Well, I don't need that one up at the top, do I? I can just put that down here if I'm going to be really mean. Alright. Traits. So trait is in scope, so we need to bring future into scope, basically. Phantom data is not defined. Man, oh man. One upside of all of this, I am at long last, starting to remember some of these namespaces. Like, I used to have to look up the namespace for Phantom data every time I used it. Alright, it's running. Maybe this is a good time to crack open a beer or something. I swear that's a sound effect, I didn't actually do that. So, it takes like 10 seconds-ish, and it finally spits something out. I'm going to change that to 5 seconds. And what it spits out is basically just the default message because it gives up waiting. That's exactly as we expected. And measure command, if you didn't know, is just a timer. And it says that it took like 6.36 seconds. Of course, that was some, some of that time was the time spent recompiling because I forgot that I made a change. Alright, 5 seconds, 343 milliseconds. Sounds good to me. So, we can make a timeout future. Now we have a little bit more complicated one to make. We're supposed to replace futures empty with something that theoretically will return your name if you type it in on the command line. So let's get started on that one. I had a really complicated design for this at first. It did not work very well, I didn't think. I mean, it involved a lot of extra memory allocations, and I really didn't enjoy the fact that I did that. I was quite ashamed. Anyways, I was looking at the same problem from a little bit different perspective as I was trying to type a post asking for advice on how to do this, and it just suddenly hit me that I didn't have to do any of the crap I was doing, and now it's a lot simpler, so hooray! I'm going to call it read line because I'm uncreative. And that's all there is to it. I'm going to set up a receiver. Oops, sync MPSC. Then you'll see why here in a minute. Apparently this means multiple producer, single something. Single receiver channel, I think. So to create a read line, we just do this. And since we have a new with this, takes in no whatevers, I think we can also do this. No, we can't, because what that does is it tries to set everything as a default, and there's no default implementation for this. I was going to try and derive default, but there's no reason to. You'd have to implement it yourself and then just call new. So create a new MPSC channel, and then spawn a thread, not even kidding, that takes the transmitter end of the channel and sends through your data. That's it. We'll then make up a read line out of just the receiving end of the channel, and we'll just return that. I believe I need to add one more. Oh, use standard thread. There we go. So this should build at this point, I think. Oh, yeah. Unresolved read line. Oops. Read line is not a particularly complicated method. I don't do it all that often, but we lock standard input. We read a line of input to a buffer. And we return either the error message or the buffer. Pretty much it. Build? And it builds, hooray! Alright, so what we're missing here, of course, is the polling implementation. So let's go ahead and do that. Our item type this time is going to be string, hard-coded, not type parameter. Our error type parameter is still going to be IO error. And of course, we have to have those same imports inside this method because we're going to use them in exactly the same way. But instead of just waiting for the time to be done, we're going to say self-receive, try, receive, and we have a little bit more complicated error okay type stuff here. In the event that we get an error back from the receive, we're going to go through the park this and come back later rigmarole. we actually have two, not one, but two, OK cases. The first being, well, I mean, there's not an order, but if we got an actual string, we'll just unwrap that, send it back to the caller as ready, and it's not actually result. I mean, it is a line. And here's the IO error case, which we'll just send straight through after, you know, unwrapping it from this OK thing here. I think this is it. It's a lot simpler after I did my homework. Where are we at on time? 31 minutes? It's not too long for something like this. It's not short, don't get me wrong. I ain't saying it's short. Alright, so if we're going to use that, we come over here, type in and we replace futures empty with readline new. And what that should do is get rid of this never returning nonsense and replace it with something that will eventually return. Let's give it a shot. Oh. No comment. Let's talk about mapping these things real quick. Can we do a map? How about that? Oh. Borrowed value only valid until here. I hate you. So we can do a map, but not like that. Obviously, the easy way to do that would be name.trim there. You know you've arrived when people say the in front of your name, right? Like hello, the rock, etc., etc. So if we don't say anything, I keep changing this value. I should stop changing this value. If we don't say anything, the timeout duration should still kick in, because we haven't actually changed anything about this stuff. We've only changed which future we're using to compose the two, right? Hello, whatever your name is. And that's it. That's all there is to that. Yeah, now that I understand what I'm looking at, I actually feel a little bit bad that this took me 2 weeks to churn out, but I think that the results were kind of worth it. The big thing about all of this is, of course, like most things in the Rust ecosystem, there is a huge emphasis on efficiency, on ensuring that when you compile with optimizations on for release mode or whatever, all of this crazy trait stuff that makes this simple read goes away, and it all becomes straightforward static calls, usually inlined. So there's no wasted time on any of this stuff. It's intended to be efficient. It's intended to be, as Mr. Crichton says, zero overhead. So that's the major difference between this kind of an implementation of futures and what you'll see in a lot of other languages. Like, for example, C#, it's a terrible idea to use a task for something if that task is going to be short, because there's a lot of time involved in setting it up and a lot of time involved in setting it down, and if the task itself doesn't take a significant amount of time, the overhead involved is going to kill any benefit you get out of doing it. Now, obviously, this is going to involve some measure of overhead over just doing it the old-fashioned way. Like, for example, we're creating a timeout struct, and this contains 3 different fields. We're creating this input struct, which basically consists of, you know, a thread and a receiver. So there is a cost here, but it's a very straightforward cost. There's not additional overhead on top of the primitives that you just created, if that makes sense. Hopefully that makes sense. One of these days, I'll get around to making a some way to compare this to C#, and it should be entertaining. One thing about this though, what I just wrote here, at no point did I run this program, even while I was trying to sort out how it worked. At no point did I run this and have it blow up in my face. If I had done this in C#, I haven't yet, but when I do, even understanding exactly what I'm trying to accomplish, I am sure that at some point or another it's going to blow up in my face and do something really stupid. The Rust compiler is never actually going to let that happen as far as this is concerned. I was actually surprised that it let me create this thread so easily, because I was like, huh, I don't know what that's attached to. I don't know what its lifetime is or anything like that, but it seems to be happy with it existing. So if it's happy, I'm happy. That's kind of how I feel about it. Anyway, I'm going to stop yammering, and I'll catch you guys next time around. Take it easy.